Welcome, my dear students. Here we have another video of our discussion. Let's be together. Now I will introduce you the third property of the chord, light. And this is about the equal chords. What you should know about the equal chords is that all chords which are equal, the equidistance from the center. Meaning to say, if I can have a circle like this one here, and you happen that you have good chords which are equal. They can start from any point to the other, as far as say maybe A, B is equal to D, X. What should expect that the distances of the chords from the center, like say O to X and O to N. These are the distances. The line ON must be equal to line OX. That's what is referred here. Equal chords, meaning that if AB is equal to DX, we should expect that that's a what? OX. Oh, no, let me use a different letter here. Y, that is talk of the AB is equal to DY. Then we should expect OX being equal to what? ON. And the converse is true. That is to say, if OX is equal to ON, therefore, AB is equal to DY. So let us try now have a proof for this property. Is it really true that if AB is equal to DY, then ON is equal to OX? That is, equal chords are equidistant from the center of the circle. Right. So here are the criteria that will help us to show this. So as I said earlier, but the first thing you do in the proof, you have to construct a diagram. So I'll consider this is my statement. That's the proof I will need to, this is just a property that I need to prove. And we'll now be drawing the diagram. Always consider a circle of this kind here. I'll have a circle here, has got a center O. Right, so in my diagram, what is that I want to show? Equal chords are equidistant from the center. So in diagram manner, how do I present this? It'll be like here, I'll draw a chord like this one here. Let's call this one as BN, and another chord here. Let's have this one as TH, like that. That's the chord. So we take that say BN is equal to TH. So what we want to show is that O to maybe talk over Q is the same as O to maybe point V. We consider OQ and OV as distances from the center. So from what I said again, if talk of a distance from the center, we expect that those two lines must be perpendicular to each to the chord. This one is perpendicular to BN because it's the distance from the center to the chord. And again, this one is expected to be perpendicular to what? TH, because it's the distance from the center to the chord. So we're there going to prove if OQ is equal to OV as such. So now, here, I would like that one this way to prove that OQ is equal to what? OV. That's it. Equal chords are equidistant from the center. Taking for granted that BN is equal to TH. Right. So once we have done that, let us at least consider some kind of construction. Add information here. Here, what we want you to do, just join the two radii to the center of the circle. So like here, I may choose to have O connected to N to form the radius and O connected to H from the radius. Right. So here we have got H joined to O and also N joined to O. Like. So here I would like that one to say join that is N and H to center O, so that we should have two radii. Right. Now, here, the moment I have got this radii, then that is enough for I to show that OQ is equal to OV. Why? The connection of the two has already given me direction. What's the direction? Having joined ON and OH, I can see that the certain shape has brought us two triangles which are right angled. Triangle OQN and triangle OVH. such that mathematically I was joining the line thinking the moment I was joining this one to say what we have here, the moment I have the triangle, then I can prove that the two triangles are what? Congruent. If I show that the two triangles ONQ and OHV are congruent, then I'll be able to pick out the corresponding sides, and I expect that the two corresponding sides will be this one and this one. And this one, if the two sides are equal, then definitely the distances from the center are equal sides. So in short, the moment I've joined ON and OV, I have got two triangles OVH and OQN, of which I'll use congruency method to prove that these two sides are equal. Right, so now let's get into business. Proof. Right, I've already detected the method that will help me to show that this is this one. It's by congruency. So what I have here, I have the two triangles which prove the congruent. So here I'll talk of the in triangle O and talk of a Q and the triangle O HV in that order. We go by sides which look to be corresponding to each other. This one corresponds to this, and this one corresponds to this, and this one corresponds to this one out. Right, so let's prove that the two triangles are congruent. So by the virtue of the look of the two triangles, I'll be able to choose a test which will go by what is given in there. You'd see that in the two triangles here, we have got this side here, the radius must be equal to this side. And this angle here is right angled in this triangle, and then that angle is also right angled. So you see that I talk of this side and that side, those are right angle. These ones are what? Hypotenuse sides of the triangle. And again, I talk of this angle and this angle, these are right angled. And again, if I can also go further to have the last classification of a side, I'll be able to see that if BN is a chord that is having a distance O Q meeting BN at Q, I expect that OQ has to bisect BN. As such, this side, that's talk of the BQ should be equal to what? And talk of what? NQ. Right. Why? OQ is bisecting BN by the first one property. So here I expect this side here to be equal to that other side. OQ is bisecting BN. The same on the other side. I also expect that, say, OV should bisect what? TH. Because OV is perpendicular to TH, is the distance from the center to the chord. So here I also expect that this one here should also be equal to that side. But now, this chord is equal to this chord. You see, equal chords. Then I expect the distance from here up that should be equal from here up that, the same as from here up that, equal to that one. So it's just like NQ is equal to Q, B is equal to T, V is equal to VH. Like that. Right. Why? These are equal chords. BN is equal to TH. So if this one is bisected, the two parts are equal. And this one is bisected, the two parts are equal. It means all the four parts must be equal to each other. Right. So we expect that, say, QN being equal to HV in the other triangle as such. Right. So let us write that. Then we decide what test are we going to use in this case. Right. So here I'll have this one. I'll talk of the side. Talk of. Let me just begin with the angle, which is the right angle there, so that maybe I can try to test the RHS if that one can work. Right. So I begin with the R as the test for the congruency. Here the R represents the right angles. Does the two triangles contain the right angle? So like in this case, if I go by this test, it means I will really see that the two triangles have got right angles in here. So here I'll write, I can present these angles by maybe letter X. This is X1, this is X2. I'll write here as to say in the triangles, X1 is equal to X2, which is 90 degrees. This is given. Right. So if I'm to consider this test RHS, it means R has been satisfied. The H tells us if the triangles have got the hypotenuse side, and these hypotenuse sides are equal. Is it shown here? Yes. you'd see that this OH is a radius, but it's a hypotenuse side to this triangle. The same ON is a radius by hypotenuse side to this triangle here. We know that radii are equal. Therefore, it means H above the H has also been satisfied. Here you just write what? O, talk of, that's you talk of ON is equal to, that is OH. Reason, radii. Lastly, let me see if I've got any one side, any one corresponding side are equal in the two triangles. So I would see here by what I've explained here. I may not like this one down here, but we can just discuss here. Look at this. BN is equal to TH, equal chords. This one is bisected to produce this side, QN being into QB. Fine. And again here, considering that the two chords are equal, this line again, OV, is also what? Is also bisecting TH here, giving us that HV should be equal to what? TV. So, since these two chords are equal as explained earlier, we should expect that VH is equal to what? QN. Right. They're coming from what? Equal chords. So, we're also going to write here to say, talk of the QN is equal to HV. Right? Listen, you talk of say BN is equal to TH. So they're bisected similarly. Right. So that's the way it goes here. So here I have got three tests which are satisfying the RHS. RHS. Hence, I'll be able to consider that I have got the RHS which is defining up a test for the congruency here. Then I expect at the end to have the two triangles being congruent. So what I'll write here is just like now, more like a conclusion based on the statement 1, statement 2, and statement 3 in the RHS as follows. So I'll write that say, therefore, triangle O and Q must be congruent to triangle that is OHV. Reason RHS. That's the way it goes. So now, if this is true, then we expect the corresponding sides again to be equal. That's because we know that the corresponding, we talk of the when triangles are congruent, we expect the corresponding angles to be equal and also the corresponding sides to be equal. If these are not equal, then the triangles can be congruent. So in such the case, then we are going to have our ON in that order is equal to OH. ON is equal to OH. And write here as the corresponding sides of congruent triangles. Then here we have shown that OQ is equal to OV. As simple as that. So each time we have, let us now buy this as the real property of the chord. That say equal chords are really equidistant from the center of the circle. Just use RHS to prove that. Right. So conversely, we can just have the opposite of which said now, if the two chords are equidistant, then it means the chords are equal. Here, I will just explain it here and there on the other side of the converse of which we have this. Right. In case you might be asked to prove the opposite way, that say now you have the chords which are equidistant. How can you prove that the chords are equal? Right. So in the converse of the first property of say equal chords are equidistant, now the reverse is true of saying that say chords which are equidistant, meaning to say here we have got a chord here like AB, another chord here like TX for the first one, and we are told that these chords are equidistant from the center. That say this line is equal to that line. That is what is referred here in this property. Right. What is the expectation of this line AB and TX? Right. So here we are told that say the chords will be equal as well if the distance from the center are equal. Right. So for you to show this one, it's very easy. I will not be in the position to write in the order of the steps, because I know you're already aware on how best you can present your work. That's logically, you go begin by given, talk over to prove, things like that, you go on. But here I'll just go straight into explanation and give you a guide on how best you can show that the two chords are equal if the distance from the centers are equal. Like, so let's have OM and OD being equal to each other. Right. So the target here is simply to just show that AB, right, to show that what AB is equal to TX. So the explanation of which we'll just do this is similar to what we did earlier. Join your O to B, O to X, things like that. Once you connect, prove that the two triangles OMB and ODX are what? Congruent. Then try to depict out the sides which are corresponding to each other. So it'd be like, the moment you connect this one out, you'll be able to see that this side here is equal to that side, that is done. And this side here is given as that side. As what? Sides which are distances which are equal, right? So it means you have got two tests already there, that this is equal to this one, and this one is equal to this one, and this one is equal to that one. Let me write it for you here. On the part of the proof, in the two triangles, in triangle that is OMP and the triangle that is the ODX, right? What we have there, we have OB, OB is equal to OX, those are the die, you go like that. And again, we're also going to mention that the OM is given as what? That's the OD. Why? These are given sides. We see that equidistant. Then the chords must also be equal. Right. Then what do you have? This angle here, OMB. Angle OMB is equal to angle what? Talk of the ODX. Angle ODX, which is 90 degrees right angle. That is also given. Right. So the three tests here are able to be satisfied in one of the condition of the congruency. Right. So you go like side, 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 angle, side. Or say you can go by what? RHS, RHS. If you can arrange this order, you can arrange the test in order. But you suppose if you like to use the RHS, you can begin by writing this here information of right angle. Then you go for the issue about the die, you talk of R, H, then S. So it's up to you that one. But if not that one, you can use SAS, where you go by side, angle, side. The two tests here are satisfied. So it's up to you which one to use as far as you write the statements in the logical order according to the arrangement of the letters in the test of the what? Of the congruency. Right, so by that, then we're able to deduce that the two triangles are also what? Congruent. Right, you can use SAS, you can use RHS, I've already explained. So you'll be able to tell that, say, triangle that is OMB will also be congruent to triangle what? ODX. Right, so if that is true, then we expect side MB, the target now should be like in the two triangles here, if they are congruent. The target will be like checking if side MB is the same as side what? That DX. If MB is equal to DX, then definitely mark that MB is half of AB. Then we expect that again, the MB should also be half of what? TX. In short, if this one will be X, this one will be X. But this is double X. So it means from here up to that, it will be 2X. And from here up to that, it will also be what? 2X as such. Right. So what we have there in the conclusion, if we are testing, is this side is equal to that side. So by the congruency here, you see that by the order of letters, that is also true. You talk of the MB and dx in that order, you see they're equal. So you're going to state here to say MB is equal to d what? X as such. Right. So MB is equal to dx. Why? These are corresponding sides of congruent triangles. Right. So the target here, the essence, just a matter of proving this side equal to this side. Right. So that's it here. So here they are really equal. So if those are equal, my explanation is clear that you expect that say 2, that is MB, is equal to 2. What? That is what? 2 dx. Right. So if 2 is equal to 2 MB is equal to 2 dx, then definitely what we have for the 2 MB, this one give us what? AB. You can see here 2 MB is equal to AB, right? And the same 2 dx, it gives us what? Tx in this case, Tx. Then at the end, this has already been what? Proved like that. So here we expect that the AB will be equal to Tx, and the AB and Tx are the chords we give our definition in this case. Right, so that's the way you can show the converse of the first property of circle, that talks about the equal chords are equidistant from the center. It means the opposite is true. If the chords are equidistant from the center, then the chords must also be equal to each other. In all circumstances, just to give you a guide, use the congruency to prove the two properties out. Right, so by this, we end again the discussion in the video. In the next meeting, we are there going to look at some problems which are related to the two properties we have just discussed. Right, so thank you for being together, and we have to meet again in the other video to come.